When you flip the switch on the wall, here is what most people imagine. A great rushing crowd of electrons leaps out of the power station, sprints down the copper wire at the speed of light, slams into the filament of the bulb, and that is what makes the light come on. That is the picture I was taught when I was a kid. That is the picture in most textbooks. That is, I am willing to bet, the picture in your head right now, even if you have never sat down to think about it. It is wrong. Almost completely wrong. Now, I am not saying the people who teach it that way are stupid. They are not. They are trying to give you a useful image. They are also mostly trying to spare you from a question that turns out to be a great deal stranger than anyone wants to admit. Because the actual answer, when you finally chase it down, makes a hash of the picture and replaces it with something so peculiar that even the physicists who first worked it out had trouble believing themselves. So let me tell you what is really going on in that wire. The electrons in the copper, the ones supposedly carrying the current to your light bulb, are moving slower than a person walks down the street, slower than you stroll to the kitchen for a glass of water. In some wires, slower than a snail. And yet when you flip the switch, the bulb lights up at once. Not slowly. Not after a delay you could measure with a stopwatch. The instant your finger closes the contact, the room is bright. How can both of those things be true at the same time? That is the puzzle. By the time we untangle it, you are going to have learned something about electricity that almost nobody learns properly. Even people who fix appliances for a living. You are going to learn where the energy actually goes when it travels from the wall to your lamp. And I promise you, it is not where you think. But before we tear the wrong idea down, let me give it a fair hearing. Because before we can throw it away, we have to understand why so many smart people believed it for so long, and why it is still very nearly believable today. Look at it from the outside, the way our great-grandparents looked at it. You flip a switch. A bulb lights up. The wire connecting them is made of copper. Inside copper, there are electrons. We have known since the late 1890s, since the work of Joseph John Thomson over in Cambridge, that what we call electric current is in fact electrons in motion. Before that, people thought of electricity as some kind of fluid, like water flowing in a pipe. They had two competing theories about which way it flowed, in fact, and they could not settle the matter for nearly a century. But Thomson and his colleagues finally pinned it down. Electricity is not a fluid. It is little particles. Tiny, light, negatively charged particles. Electrons. So if current is electrons in motion, and the current shows up at the bulb instantly, then the electrons must be moving incredibly fast. They have to be. There is no other way for the message to get there. Right? If you think about it that way, every piece fits beautifully. Electrical signals in your house come on the moment you call for them. Telegraph operators were sending messages across continents in fractions of a second by the 1860s. They strung undersea cables across the Atlantic Ocean and pushed signals through them from Ireland to Newfoundland. Whatever was carrying those signals had to be flying along at tremendous speed. The natural conclusion: the electrons themselves are racing through the wire near the speed of light. And actually, here is where the picture gets even more tempting, because it picks up some real physics on the way. Inside a piece of copper, the electrons really are moving fast. I mean really fast. Their thermal speed, the speed they zip around at simply because the metal is warm, is something like 1,000,000 meters per second. 1,000,000. That is 10,000 times faster than walking. It is faster than a rifle bullet. It is faster than the space shuttle in orbit. Faster than the moon orbits the Earth. So if somebody comes along and says the electrons inside a wire are extremely fast little things, you can absolutely back that up with real physics. They are. Put it all together and we have a tidy little story. Electrons are fast. Electrons carry the current. The current arrives instantly. Therefore, the electrons themselves race through the wire from one end to the other, and that, my fellow human being, is how electricity works. Comfortable? Good. Now let me ruin it. That thermal speed I just mentioned, the 1,000,000 meters per second, has a nasty little asterisk attached to it. The electrons in a copper wire are indeed zipping around at fantastic speed, but they are zipping in completely random directions. Up, down, sideways, banging into atoms, bouncing off, doubling back. Like a swarm of bees the size of a city. Every bee buzzing in some private direction. Every bee occasionally crashing into one of its neighbors. From outside the swarm, the whole thing looks still. The bees are not going anywhere. They are just buzzing. The average velocity of all those electrons, when you add up everybody's wild directions, is essentially zero. They are not net traveling anywhere. They are just churning. When you turn on a current, you do not crank up the chaotic speed. They are already doing 1,000,000 meters per second in random directions. What the current does is something much more subtle. It gives them a tiny, tiny bias, a faint preference for one direction over the other. They keep churning chaotically, but on top of all that wild motion, on average they drift very slowly toward the bulb. Every electron slightly favoring one direction over the others. How slowly does this drift happen? Let me actually compute it, because this is one of those numbers that, if you have never seen it, will absolutely floor you. Take a normal copper wire, the kind running through your wall. Say it has a cross-section of about 1 square millimeter. That is a thin wire, about the thickness of a thick pencil lead. And let us say the wire is carrying 1 ampere of current. 1 amp. That is a typical household current, the kind a small lamp would draw, or a clock radio, or one of those little fans on a hot day. Now, how many electrons are in that wire, ready to take part in the current? In copper, every atom contributes about 1 free electron, an electron that is not stuck to a particular atom but wanders around the metal. Atoms in copper are packed in tight, the way oranges are packed in a crate. The number of free electrons works out to roughly 8 times 10 to the 28th electrons per cubic meter. That is an 8 followed by 28 zeros per cubic meter. In 1 cubic millimeter, which is the cross-section of our wire times 1 millimeter of length, you still have something like 8 times 10 to the 19 of these free electrons. An ungodly number. More electrons than there are stars in the observable universe, sitting in a piece of wire smaller than a grain of rice. 1 ampere of current means 1 coulomb of charge passes any given spot every second. 1 coulomb, when you count it up in electrons, comes to about 6 times 10 to the 18th of them per second. That sounds like a lot. It is a lot. 6 billion electrons go past every second when you have 1 amp of current in a wire. Now here is where the trick happens. You have 8 times 10 to the 19 electrons in each cubic millimeter of the wire, and you only need 6 times 10 to the 18 to pass the spot in a second. Divide one by the other, and you find out, on average, how fast each electron has to be moving in order to keep up with the current. It comes out to roughly 7/100ths of a millimeter per second. 7/100ths of a millimeter per second. Let me put that in human terms, because the number alone is hard to feel. A garden snail crawls at about 1 millimeter per second, so the electrons inside your wires are moving about 14 times slower than a snail. A walking person moves at maybe 1.5 meters per second. The electrons are about 20,000 times slower than that. If an electron in the wire next to you started traveling toward your light bulb the moment you flipped the switch, and the bulb were just 1 meter away, it would take that electron more than 4 hours to get there. 4 hours. 4 hours from the switch to the bulb. So if our cozy little story were correct, if the lamp lights up because the electrons travel from the switch to the bulb, then every time you reached out to flip a switch, you would have to settle in with a book and wait until lunch was finished cooking to read by your new lamp. But you do not. You flip the switch and the bulb lights up at once, within 1/1000th of a second, sometimes faster. So something is wrong with our story. Profoundly wrong. The picture has a hole in it the size of a house. This is the place where students get nervous, because we have just thrown out the most natural explanation for how electricity works, and we have not yet given you a new one. The electrons are slow. The signal is fast. What in the world is doing the work? For a moment you might be tempted to say, well, maybe it is not the same electrons all the way down. Maybe one electron pushes the next, like billiard balls in a row, and the push propagates through the line. And that is closer. That is getting warmer. The image of a row of billiard balls is at least the right shape. But it is still not quite right, and the thing that is missing when you finally find it is going to change the way you look at every appliance in your house, every wall socket, every cord on a lamp. Let me give you an analogy that captures part of what is happening, and then I am going to push you past it to the real picture. Imagine a garden hose, a long one, already full of water, end to end, no air bubbles. You turn on the spigot at one end. What happens at the nozzle on the other end? Water comes out, and it comes out almost immediately, long before any individual molecule of water from the spigot has had time to travel the length of the hose. The water that comes flying out of the nozzle in that first moment is the water that was already sitting near the nozzle. It got pushed out by the water behind it, which got pushed by the water behind that, and so on all the way back to the spigot. The push traveled fast through the water. The water itself moved slow. That is a piece of what is happening in a wire. The electrons are already there, all along the wire, sitting in copper, doing their thermal jiggling. When you flip the switch, you do not send fresh electrons in from one end to be delivered to the other. You apply a force, an electric field, that pushes on every electron in the wire at once, or nearly at once. The push spreads through the wire at something close to the speed of light. And every electron starts drifting in response, not because the original electron has reached it, but because the force has reached it. So part of the answer is that the wire is already loaded. Every cubic millimeter is packed with charge carriers, ready to start drifting the moment they are pushed. The signal that flips the switch and lights the bulb is not a stampede of electrons, but a wave of pressure, a propagating push, that arrives at the lamp far before any individual electron does. That is a beautiful picture. As far as it goes, it is correct. But if I left it there, I would be cheating you. Because the strangest, most beautiful piece of this puzzle is still to come, and I do not want you to leave without it. What is the push? What carries it through the wire? Most people, when they hear the words electric field, picture something inside the wire. A force traveling along the copper, from the switch to the bulb, like a surge of invisible juice slipping through the metal. That is how I was taught in school. The electric field, they said, is in the wire, pushing the electrons along. Now I am going to tell you something that you might want to sit down for. The electric field that is doing the actual work, the field that carries the energy from your battery to your light bulb, is not really inside the wire at all. Or rather, it is not where the action is. Let me build that up carefully, because it is one of the strangest facts in physics, and I do not want you to nod along and miss it. When you set up a circuit, a battery and a wire and a bulb, you do not just create motion of charges. You create electric and magnetic fields. The electric field is created by the charges in the wire. The magnetic field is created by the moving charges. Both fields fill the space around the wire. They are not just inside it. They are everywhere outside it too. They reach out into the air around the wire, they reach across your room, they reach through the walls. They drop off with distance, of course, but they are out there. The field is not confined to the conductor. The field is in space. A long time ago, around the 1880s, an Englishman named John Henry Poynting, working on Maxwell's equations, figured out something extraordinary. He showed that you could actually calculate the flow of energy in any electromagnetic field. He worked out where it goes, and how much of it goes there. The energy, he found, moves in the direction perpendicular to both the electric field and the magnetic field. There is a recipe. You point your fingers along the electric field, you curl them toward the magnetic field, and your thumb shows the direction the energy is flowing. Apply this recipe to a simple circuit, a wire carrying current to a bulb, and you get a result that is, I have to warn you, extremely strange. The energy is not flowing through the wire. The energy is flowing through the space around the wire. It is flowing through the air. It is flowing through the gap between the wires. It is flowing through the empty space that surrounds the cord. The energy comes out of the battery, it travels through the empty air around the cord, and it pours into the lamp from outside, from the space around the bulb. The wire is not a pipe carrying the energy. The wire is a guide. The wire shapes where the field goes. The energy is carried by the field, in the space around the wire. Now I know this sounds like I am playing some kind of trick on you, so let me make it concrete, because the math really does say this. If I have a battery, and a wire going from the battery to a light bulb and another wire going back, the energy from the battery does not squirt through the wires like water through a hose. The energy launches into the space around the wires. It travels through the air, through the gap between the wires, around the bulb. The wires guide it. The wires shape its path, but the energy itself is in the field outside. You can prove this by computing the Poynting vector at every point in space around the circuit. Poynting did. Heaviside did, independently, working in obscurity in his brother's house in Devon, scribbling equations and arguing with everybody. The conclusion is robust. The flow of energy in any electrical circuit goes through the space outside the conductors, not through the conductors themselves. This is, by the way, why electrical engineers worry about something called impedance, and why the geometry of cables matters so much. It is not just about how good a conductor the metal is. It is about how the cables shape the fields in the space around them. A coaxial cable, the kind people use to hook up televisions to outside antennas, has an outer cylindrical shell and an inner wire running down the middle, with insulating material between them. The energy in such a cable flows in the space between the inner wire and the outer shell, through the insulator, in the field. The wires themselves are just there to define the geometry. They tell the field, here is where to go. Here is the channel I want you to follow. For your house wiring, the situation is exactly the same, even though it is not arranged so neatly. The current flows in the wires. The energy flows in the air and the plastic insulation around them. The wires steer it. The lamp catches it. And this is why, when you flip the switch, the lamp comes on right away. Not because the electrons are fast. They are absurdly slow. And not just because the push propagates through them, though that is part of the story. The lamp comes on because the field, which is established almost at the speed of light, fills the space around the circuit and starts dumping energy into the bulb the moment the circuit is closed. The signal travels at near light speed, because electromagnetic fields travel at light speed. That is what they do. They are disturbances in the structure of space itself. And the wire is just there to tell them where to go. Let me back up and give you the whole picture in one piece, because there are layers here that I want to put in their proper order. Inside the copper wire, you have a sea of electrons. They are moving fantastically fast, about 1,000,000 meters per second, in completely random directions. Picture a swarm of bees the size of a city, every bee zipping around chaotically. From outside, the swarm looks still. The bees are not going anywhere on average. They are just buzzing. Now imagine a gentle wind blowing through the swarm. Each bee keeps doing its private buzzing, but on top of that random motion, there is a slight bias. They drift, very slightly, in the direction of the wind. The wind is gentle, and the drift is slow. But it is there.